This is an AQA GCSE Chemistry Paper 2 from June 21. This question is about fuels and energy. Figure 1 shows the percentage of electricity generated in the UK between 2007 and 2017 using oil and solar energy. Okay, so over time, oil use has decreased, solar energy has increased. Describe the changes in the percentage of electricity generated in the UK between 2007 and 2017 using oil and solar energy, and use data from figure 1 in your answer. So let's pull out some actual numbers down here. So looking at solar energy down here, we've gone from around 0% to 3.4%. So let's write about that first. Let's write some corresponding figures for oil. So here it's 1.3% down to 0.5%. But look, in terms of the oil use, it did actually increase from 2007 to 2009. Oil contains carbon and some sulfur. When oil is burned, the products of combustion may be released into the atmosphere. Explain the environmental effects of releasing these products of combustion into the atmosphere. It's worth 6 marks. So let's divide our answer into the issues that come from burning the carbon. Remember, that produces carbon dioxide and carbon monoxide, so we'll talk about those separately. And then the sulfur impurities produce sulfur dioxide, which dissolves, forming acid rain. So we've got lots to talk about here. So let's start with burning carbon. What's wrong with releasing carbon dioxide? Carbon dioxide is a greenhouse gas which contributes to global warming. So we're cramming our answer full of detail here. And we can even write a lot about what happens with global warming. Polar ice caps melt. Sea levels rise. There's habitat destruction. And as a result, loss of biodiversity. So very full answer there relating to carbon dioxide. Carbon monoxide may also be released. Why is that an issue? Because remember, carbon monoxide is toxic. You could talk about, with incomplete combustion, that actual carbon is released, which remember is soot, which causes global dimming. But now I want to turn our attention to sulfur. Sulfur impurities in that oil produce sulfur dioxide when burnt. Remember, you can write these formulae out in full. And that SO2 dissolves in rainwater to form acid rain. And so many things we can talk about with acid rain. Acid rain dissolves limestone buildings, damages trees, makes lakes too acidic for aquatic animals. Suggest one reason why using solar energy is a more sustainable way of generating electricity than burning oil, because solar is a renewable energy source. Solar energy may not be able to replace the generation of electricity from fossil fuels completely. Suggest 2 reasons why. First of all, because it's very dependent on the sun, which is obviously extremely unreliable. And secondly, solar panels are fairly inefficient, so you need a huge amount of land in order to place all the solar panels you'd need. This question is about alkanes. Table 1 shows some info about alkanes. Plot the data from Table 1 on Figure 2. Number of carbon atoms 4, boiling point 0. 5, 36. 6, 69. 8, 126. 9, 151. Predict the boiling point X of the alkane with 7 carbon atoms in a molecule. So what you have to do is draw a line up from 7 and then read across on that y-axis. to get a value of around 93. They will accept a range of answers here based on the fact that everyone's graphs will be drawn slightly differently. Figure 2 is not suitable to show the boiling point of an alkane with 3 carbon atoms in a molecule. Suggest one reason why. You'd expect it to have a minus degrees Celsius, so our graph line doesn't really go that low, does it, down here? What is the state at 20 degrees Celsius of the alkane with 4 carbon atoms in a molecule? So we know it boiled at 0 degrees, which means it's turned into a gas. So it'd still be a gas at 20 degrees. Table 1 is repeated below. The alkane with 9 carbon atoms is called nonane. Complete the formula of nonane. So we use this general formula where, in this case, n is 9. What's 2 times 9? 18, plus 2 is 20. Nonane will condense lower in a fractionating column during fractional distillation than the other alkanes shown in Table 1. Explain why. You should refer to the temperature gradient in the fractionating column. The temperature gradient refers to the fact that it is hotter at the bottom of the fractionating column. And because nonane has a higher boiling point, because remember, it's got more carbon atoms, it will condense at the bottom. This question is about paper chromatography. A food colouring contains a dye. Plan an investigation to determine the RF value for the dye in this food colouring. Your plan should include the use of a beaker, solvent, chromatography paper. So what I've drawn so far, here's your beaker, here's your filter paper, which you hang off the pencil. You need a reference line, which we draw in pencil because that's insoluble. Then you add your spot of dye, and then remember you need to dip your paper in your solvent, which tends to be water. It could be alcohol, to be fair. But that just also needs dipping lower than the reference line so that when it starts soaking up the paper, it will draw your ink dot up with it. So remember, in order to find the RF value, you want to measure the distance moved by the dye, and then you also want to measure the distance moved by the solvent. And both of these need to be from the reference line. And then when you substitute those into this equation, you'll be able to find the RF value. Obviously, feel free to kind of point out a bit more of the method here, but as long as you've drawn it properly and labelled it, I can't see how they'd have any issues. 2 students investigated a dye in a food colouring using paper chromatography. Each student did the investigation differently. The RF values they determined for the same dye were different. How did the students' investigations differ? Tick 1 box. Should be the solvent. That would really affect how far these dyes moved. Paper chromatography involves a stationary phase. What is the stationary phase in paper chromatography? So this is really weird, but because the stationary phase isn't a time frame, it's actually a noun. It's the thing which isn't moving at any point during your experiment, which means it's the paper. This question is about polyethylene and polyesters. Polyethylene is produced from ethene. Figure 3 shows part of the displayed structural formula equation for the reaction. Complete figure 3. So when you draw these addition polymerization equations, remember we break that double bond and it becomes single. And then we show that we have lots of units by adding an N. Polyethylene is a thermosoftening polymer. Suggests why polyethylene is easier to recycle than thermosetting polymers. The fact that they're thermosoftening means that they can melt and therefore be easily reshaped into new products. Ethene produces different forms of polyethylene. How can different forms of polyethylene be produced from ethene? Through the use of different temperatures or pressures. Two different forms of polyethylene are high density HDP, low density LDP. Look at the structures. Explain why HDP has a higher density than LDP. We can see that the HDP is arranged in lengths or in strands, which means they compact together quite tightly in order to increase the density, whereas you've got a much more jumbled mix of polymer chains for LDP. and therefore you'd have fewer molecules per unit volume of LDP. And the reason we're talking about per unit volume is, remember, the equation for density is mass divided by volume. So we do need to take volume into account when answering this. Figure 5 shows 3 monomers A, B and C. Monomer A can react with monomer B and with C to produce polyesters. Remember, an ester has this functional group here. Draw a circle on figure 5 around an alcohol functional group. We're looking for OH here. So there. Don't pick these ones here because remember this is a carboxylic acid. Complete table 2 to show the formula of the small molecule produced when monomer A reacts with monomer B, monomer A reacts with monomer C. So looking at A and B first of all, you have an alcohol reacting with a carboxylic acid, which remember produces an ester and water in a condensation reaction. So that's why water is your answer here. If we consider what's happening when monomer A and monomer C react, again you're going to lose the H from the alcohol and you're going to lose the Cl, this time from monomer C, so that produces HCl as a byproduct. This question is about fertilizers. Some fertilizers are described as NPK fertilizers because they contain 3 elements needed for healthy plant growth. Which 2 compounds each contain 2 of these elements? So the elements are, use your periodic table if you're not sure, nitrogen, phosphorus and potassium. Ammonium nitrate does not contain either phosphorus or potassium. Ammonium phosphate contains nitrogen and phosphorus, so that's true. Calcium chloride, absolutely not. Calcium phosphate, nope. Potassium chloride, it contains the potassium we need, but none of the others. Potassium nitrate has potassium and nitrogen in it. That's quite a weird question. Rocks containing calcium phosphate are treated with acid to produce soluble salts that can be used as fertilizers. Name the soluble salts produced when calcium phosphate reacts with nitric acid and phosphoric acid. Let's write the equation. So the salt is going to be the metal used, so calcium, and the ending on the acid, which is nitrate. Remember, all nitrates are soluble. This one's hard, but the answer is calcium dihydrogen phosphate. Ammonium sulfate is a compound in fertilizers. It can be used using an industrial process or in a lab. In an industrial process, you react streams of ammonia solution and sulfuric acid, evaporate the water by passing the solution down a warm column, collect dry crystals continuously at the bottom of the column. In the laboratory, the following steps are used. React ammonia solution and sulfuric acid in a conical flask, evaporate water from the solution until crystals form, leave to cool and crystallize further, separate the crystals using filtration, dry the crystals between pieces of filter paper, evaluate the 2 methods for producing a large mass of ammonium sulfate. Okay, so a large mass means we're producing lots of it. So what's good about this one? First of all, you can see it's going to be quicker. This is a key word. It's a continuous process rather than a batch process. Everything's made on a large scale. Evaluate tends to mean give disadvantages, but really, there are no real disadvantages here with the industrial process if, after all, what you're after is a large mass of ammonium sulfate. This question is about cycloalkenes. Cycloalkenes are ring-shaped hydrocarbon molecules containing a double carbon bond. Cycloalkenes react in a similar way to alkenes. Describe a test for the double carbon-carbon bond in cycloalkene molecules. Give a result. So remember, when we test for unsaturation for alkenes, we add bromine water. And the colour change turns from orange to colourless. Make sure you say colourless rather than clear. And that proves that you have that C double bond, C. Table 3 shows the name and formula of 3 cycloalkenes. Determine the general formula for cycloalkenes. Oh, this is like a logic puzzle. So how do we get to these numbers? Well, what you've done, I think, is if N equals your number of carbon atoms, so it goes Cn, and then how do you arrive at your H number of atoms, where you do 2 lots of your carbon atoms and then you minus 2. And just to show that it works, what about if N equals 4, like it does here, then you end up at C4H. 2 times 4 is 8, minus 2 is 6. What about if N equals 5, you end up at C5H8, and if N equals 6, you arrive at C6H10. Figure 6 shows the displayed structural formula of cyclohexene. Chlorine reacts with cyclohexene to produce a compound with this formula. Complete figure 7 to show the displayed formula. So let's add those bonds. We've got 4 hydrogens already. We need to add another 6. Remember that each carbon atom forms 4 bonds. Because we also need to add a Cl, make sure those Cl's get added to separate carbons and then complete with hydrogens. And then just add them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 hydrogens, 6 carbons, and 2 chlorines. Calculate the percentage by mass of chlorine in the molecule of this. So we do the MR of chlorine over the total MR of the compound times by 100. So we have 2 lots of chlorine, so 2 lots of 35.5. Let's work out the total MR of C6H10Cl2. So your calculation becomes 71 over 153 times by 100 to get 46.4% as your answer. Potash alum is a chemical compound. Here's its formula. Give a test to identify the group 1 metal ion in potash alum. You should include the result of the test. So your group 1 metal ion is K+. You want to use a flame test. And remember, if you have a potassium ion, you should see a lilac flame. Name one instrumental method that could identify the group 1 metal ion and show the concentration of the ion in a solution of potash alum. You would use flame emission spectroscopy here. A student identifies the other metal ion in potash alum. The student tests a solution of potash alum by adding sodium hydroxide until a change is seen. Give the result of this test. So another metal ion here is Al3+. So remember, you see a white precipitate with sodium hydroxide and aluminium ions. This test gives the same result for several metal ions. What additional step is needed so that the other metal ion in potash alum can be identified? Give the result of this additional step. So we're trying to identify another metal ion. So what you want to do is you want to add excess sodium hydroxide, and what you should find is the precipitate dissolves. Describe a test to identify the presence of sulfate ions. Give the result of the test. You have to learn all these tests. So your reagent this time is barium chloride and hydrochloric acid. And this time you should see yet again a white precipitate, which will be barium sulfate. So yeah, if you see a white precipitate, it means you have sulfate ions. This question is about copper and the alloys of copper. Solders are alloys used to join metals together. Some solders contain copper. Table 4 shows some information about 3 solders. Solder B and solder C are now used more frequently than solder A for health reasons. Suggest one reason why. Let's look at the difference then. So they all have tin and copper in. There must be a reason why we don't like using lead compared with silver. Well, it's because lead is toxic. Suggest one reasons why solders B and C have different melting points. It will be to do with the proportions of metal used, because remember, different metals have different melting points. Copper can be obtained by processing copper ores, by recycling scrap copper. Suggest 3 reasons why recycling scrap copper is a more sustainable way of obtaining copper than processing copper ores. Well, first of all, recycling conserves copper ores. Recycling means that there's less landfill. And also, The processing of copper ores needs quarrying, which causes environmental impact, so therefore recycling means that you do less mining or quarrying. Copper is extracted from low-grade ores by phytomining. Describe how copper is extracted from low-grade ores by phytomining. Remember, phytomining is all to do with plants. We start by saying grow plants on land containing low-grade ores. The plants absorb the copper in their roots. Next up, we burn the plants, and the ash produced is dissolved in acid to produce a solution containing the copper. And lastly, electrolyze that solution to obtain the copper. Phytomining has not been widely used to extract copper, suggests 2 reasons why. First of all, it needs a lot of land, so sometimes you might not have enough land available. Secondly, it takes a very long time. A student investigated how a change in concentration affects the rate of reaction between zinc and sulfuric acid. Here's the chemical equation. Pour 50 centimeters cubed of sulfuric acid of concentration 0.05 mol into a conical flask. Add 0.2 grams of zinc powder. Put the stopper in the conical flask. Measure the volume of gas collected every 30 minutes for 5 minutes. Repeat with sulfuric acid of double the concentration. Figure 8 shows the apparatus used. So this is your gas syringe that's going to be collecting your hydrogen gas. The student made an error in setting up the apparatus. What error did they make? Have a look. That delivery tube is collecting gas, so it shouldn't be in the acid. The student corrected the error, and here are the student's results. Explain why the lines of best fit on figure 9 become horizontal. So why does the amount or the volume of gas remain constant? Because the reaction has stopped as one of the reactants has been used up. How does figure 9 show that the zinc powder reacts more slowly with 0.05 mole of acid compared with 0.1? Let's label our lines. So here's our lower concentration, here's our higher concentration. What's true about these portions of the line? Well, with 0.1 molar, you can see that you have a steeper gradient. Determine the rate of reaction for 0.05 mole sulfuric acid at 80 seconds. Show your working and give your answer to 2 significant figures. So we're looking at this line. We need to show how we're working this out by drawing a line on this graph. It goes up here. So we're looking for the rate of reaction here, which means we need to draw a tangent. So we need to find the gradient of that line, which is change in y over change in x. So change in y, first of all, is 69 minus 40 over our change in x, which is 200 minus 20. And so to 2 significant figure, our value is 0.16. The activation energy for the reaction between zinc and sulfuric acid is lowered if a solution containing metal ions is added. What is the most likely formula of the metal ions added? So because we've lowered the activation energy, it means we've added a catalyst. Remember, it is transition metals which can act as catalysts. Now the transition metals sit in the middle of the periodic table, so it's copper. This question is about alkenes and alcohols. Ethene is an alkene produced from large hydrocarbon molecules. Large hydrocarbon molecules are obtained from crude oil by fractional distillation. Name the process used to produce ethene from large hydrocarbon molecules. It's known as cracking. Describe the conditions used to produce ethene from large hydrocarbon molecules. So what are the conditions needed for cracking? A high temperature and an alumina catalyst. Ethanol can be produced from ethene and steam. The equation for the reaction is this, it's exothermic. Explain how the conditions for this reaction should be chosen to produce ethanol as economically as possible. This question is all about equilibria because we have a reversible arrow there. So if the forward reaction is exothermic, that means we need to lower the temperature. Why? Because it shifts the position of equilibrium to the right, increasing the yield of ethanol. However, be careful with that temperature because remember low temperatures mean low rates of reaction. So choose a slightly higher temperature. Remember these conditions will always have to be compromised to increase the rate of reaction, as particles will have more kinetic energy and therefore there'll be an increased frequency of successful collisions. Now let's consider equilibria from a pressure point of view. So count the number of moles of gas on each side. We've got 2 moles on the left side versus 1 mole on the right. Remember, we're looking at these numbers here. So to favour more ethanol, we want to increase the pressure to move the position of equilibrium to the right. So choose high pressure, as there are fewer moles of gas on the right-hand side. So the position of equilibrium shifts to the right in favour of more ethanol. High pressures also mean high rates of reaction due to increased frequency of collisions. Ethanol can also be produced from sugar solution by adding yeast. Name this process. It is fermentation. Butanol can be produced from sugar solution by adding bacteria. Sugar solution is broken down in similar ways by bacteria and by yeast. Suggest the reaction conditions needed to produce butanol from sugar solution by adding bacteria. First of all, you want quite a warm temperature of around 37 degrees to provide the optimum temperature for the enzymes in the bacteria. And next up, we need anaerobic conditions, i.e. ones without oxygen, to enable the bacteria to anaerobically respire. Ethanol and butanol can be used as fuel for cars. A car needs an average of 1.95 kJ of energy to travel 1 metre. Ethanol has an energy content of 1300 kilojoules per mole. Calculate the number of moles of ethanol needed by the car to travel 200 kilometres. Okay, let's be a bit careful here with our units. The first thing we need to do is work out how many metres there are in 200 kilometres, and it's 200,000. So therefore, how much energy is needed to travel that 200,000 metres? Well, we take the 1.95 and multiply it by 200,000 to get 390,000 joules. And therefore, if ethanol has an energy content of 1300 kilojoules per mole, we take the number we just calculated, divide it by 1300 to get a value of 300 moles of ethanol needed. When butanol is burned in a car engine, complete combustion takes place. Write a balanced equation for the complete combustion of butanol. Remember, butanol looks like this. So let's write its molecular formula. So that's C4H9OH. Because it's complete combustion, we need a plentiful supply of oxygen, meaning that we produce carbon dioxide and water as our byproducts. And now let's balance. So how many hydrogens do we have on the left-hand side? 10. So I need a 5 here. Count up your oxygens on this side. We've got 8 plus 5, which is 13. We've got 1 on this side, which means we need to make up the remaining 12. So we need 6 O2s.